Thank you, Ala. Thank you for the invitation. So today we'll talk about construction of parabolic Hitchin connection done in my thesis. So it will be in two parts. The first part will be about Hitchin connection and motivation. After that, I will give an algebro-geometric approach to construct such connection. In the second part, I will talk about parabolic vector bundles, their moduli spaces, and some of their properties. And finally, I will give the construction of the Hitchin connection in this parabolic setting. So let's begin by the first part, where I will fix a real compact symplectic manifold. So this is due to Hitchin. He tried to give geometric quantization to a symplectic manifold. We know that geometric quantization means that we associate to your vector, to your symplectic manifold vector space up to scalar that satisfies certain properties. In this talk, we are interested on color polarization, which means the color structure on your symplectic manifold compatible with your symplectic form. And if 1/2 pi, the class of the symplectic form, is integral in the Durham cohomology group, you can give a geometric interpretation of this symplectic form to be the first Chern class of a holomorphic line bundle. So E here is a complex structure that you fix, almost complex structure, which is color on M. And the first, the line bundle is a holomorphic also with respect to this structure, and you ask that the first Chern class is exactly the class of your symplectic form. So the natural vector space that you are interested in the geometric quantization is just the global holomorphic sections. Natural question is that does the dimension of this complex vector space depend on the complex structure? And to do this, you need to understand a family of color polarization. So you take B to be parameter space and pi a holomorphic map. And M is also a complex variety where the fibers, this map, it's submersive by Ehresmann. We know that it's locally trivial. So you ask that the fibers are diffeomorphic to the symplectic manifold. And this line bundle is a family of holomorphic line bundles given as given before. So here is the global sections of the line bundle. So L restricted to the fiber is exactly the line bundle that you fixed before. You associate to this data the sheaf of global sections, which means the push forward of the line bundle using the map pi. Here it's in general it's just a coherent sheaf. The fibers are the global sections on a point B in the base are just the global sections of the line bundle restricted to the fiber over B. So what did Hitchin show? It's under some conditions on the symplectic manifold and the line bundle, you can construct a unique projective connection on the push forward. But the construction that Hitchin uses a lot of geometric differential techniques. So he gives also an important example of application where M is the character variety, G is a compact Lie group, a real Lie group. And in our case, we are interested in the case SUR. So this variety is symplectic by the Atiyah-Bott-Goldman form. And the parameter space B, he took all the Teichmüller space of genus G curves on S. So you can imagine this space to be the complex structures, if you want, on S. So S is topological orientable surface of genus greater than 2. So an element on the Teichmüller space give us a complex structure on the topological surface, which is a Riemann surface now, and you can associate another space. So for any point B, you denote the complex structure to be C subindex B. And you associate the space of holomorphic vector bundles of rank R and trivial determinant. The determinant here means that you take the top exterior product of your vector bundle. And stable here means that this vectors bundle, all the sub-vector bundles are of negative degree. So you quotient this space by this set by the isomorphism of vector bundles. This is a variety. It has very nice properties. But why we are interested in this variety? In fact, this is we have a Narasimhan-Seshadri theorem that identifies this symplectic manifold that we are interested to apply Hitchin's theorem with this variety. This is a homeomorphism. So in the left-hand side, we have a symplectic manifold, and in the right-hand side, we have an algebraic variety. So Hitchin will use a lot of algebraic properties of this variety to give a connection also on this variety over a special line bundle. I will talk about the special line bundle now. So if you fix a Riemann structure, you have a lot of properties. First one, this variety is a stable vector bundles is quasi-projective, which means it is an open set inside the projective variety. And it's also always smooth. The second property, you can compactify this variety by adding other vector bundles, which we call semi-stable, which means that all proper sub-bundles has a non-positive degree. So you can have a vector bundle and a sub-bundle of degree 0. So the degree here is the degree 0 because the trivial line bundle has degree 0. But you need to enlarge your relation. You take what we call Seshadri relation or S equivalence, but you can imagine that just by that you take isomorphism classes, but it's more than this. So this is due to GIT construction of this moduli space. So this variety now it's projective. It's a compactification of the first one, but it is also normal in general. So I mean by normal, the complementary here of the stable locus is the smooth locus, except a special case when the genus is 2 and the rank is 2, is all the smooth locus, and the complementary, it's exactly the singular locus. And normal means that this singular locus, it has codimension at least 2. And the dimension of this variety depends only on the rank and the genus of your curve. You can calculate the tangent space of this variety on a class of vector bundles. It's given by the first cohomology group with values in trussless endomorphisms. Trussless, this is because we fix the determinant. If you don't fix the determinant, you fix just the degree, you take all the endomorphisms. And if you don't know what I mean by first cohomology group with values in a vector bundle, you can just take the third duality and identify this vector space with the global sections of the trussless endomorphism twisted by the canonical line bundle, which is exactly the one holomorphic forms. And the dual here to have canonical isomorphism. This is what we call the third duality. The last important geometric property is that this moduli space has pK group reduced to Z. So this is Drese and Narasimhan theorem, and they show that the canonical line bundle is exactly -2R multiple of the generator. This line bundle, we call it the determinant line bundle. I will not give the definition here, but it depends on the degree or on the determinant that you fixed and the rank. Another remark, if you change here the trivial line bundle by any line bundle L of fixed degree D, the canonical will change, will be the generator to the power of -2, the GCD between the rank and the degree. So R here can be seen as GCD between the rank and 0. Okay. Now we are interested in a special vector bundle because we need a global vector bundle on the variety M. M here, it's a relative family of moduli spaces, which means that if you fix any Riemann surface structure, the fibers of this map pi is exactly the moduli space that I gave before. And the L is a global line bundle that has a property that its restriction to the fibers are exactly the generators of the pK group, given by Drese Narasimhan theorem. So this is M italic. It's a relative vector, a relative moduli space. It has there is theorem that shows that this moduli space exists in families. What we mean by the bundle of non-abelian theta functions is that you take the push forward of the positive kth power of your line bundle, so you will get what we call the non-abelian theta functions of level k. K is a positive integer. Equivalently, this vector bundle, we call it also the conformal blocks. This is due to the isomorphism given by Boville and Laszlo. So conformal blocks is given in another theory and came from physics, but the two vector bundles are isomorphic up to multiple scalars. So non-zero scalar. It means that the projectivization are isomorphic and not the variety, not the vector bundles. And Hitchin, what he showed, he applied the first theorem where he sees this family as a color quantization or color polarization. So he applied his theorem. He knows that there is a unique projective connection, but he shows the flatness. So he showed also that the connection that he constructs is flat. In some sense, this flatness criterion and the existence of the connection identifies the fibers of this vector projectivization of this vector bundle, as you will get the projective vector space associated to your topological surface. And this is an example of what we call the topological quantum field theory. So you have a topological space and you associate an invariant that depends only in the topology, on the topology. So if you add structure, you want to show that the object that you define is independent on this structure. So this is an example of topological quantum field theory. So just remark the work of Hitchin is based or motivated by the work of Wheaton of the topological invariant theory of 3-dimensional manifolds, and where he showed that the topological quantum field theory that he constructs give us John's polynomials of nodes. Now, as we see, all the objects here are algebraic. So the question, can we construct this connection algebraically? So without using the Atiyah-Bott symplectic form, neither the complex structure of the color structure of your variety. So now I will give an algebro-geometric approach to construct such connection. So you take any family of complex varieties. So the pi is a holomorphic, proper surjective submersive map. In algebraic geometry, submersive, we replace it by smooth map, but here I said submersive. It's the same thing in different categories, if you want. And L is a relative line bundle. Relative, it means that you identify L with any line with L twisted by any line bundle that came from B. So this is what we call the relative Picard group, if you want. And the question is, can we construct a projective connection over the push forward to any positive power of the push forward over the parameter space B? And to do this, I will give some definitions, and after that, I will tell you how to construct such connection. The first important ingredient is what we call the Kodaira-Spencer map in the deformation theory. So if you take a map like this, it's a submersive. So you have the differential map, it's a surjective map, and the kernel is what we call the relative tangent field, tangent bundle. It's the vector fields that are tangent to the fibers. If you fix any point in the base, you can define the cohomology, the first connecting homomorphism in cohomology that takes a vector bundle in the base on the point B and give you an element of this cohomology group. You need to see this cohomology group as infinitesimal deformations of your complex structure. And you can do this in globally over B, what we call the Kodaira-Spencer over B. It's just you take the cohomology with respect to the map pi in families. You take this map, but in families. So you get that you have a map that takes a vector bundle on the base and give you an element of this vector bundle on B, but the fibers here are exactly in general, not directly, but they are related to these vector spaces. And here the isomorphism, in fact, you have twist by the push forward of the trivial line bundle, but if the fiber are connected, you will have just twisted by the trivial one. So you have the relative tangent map. Okay. Now we need another tool, which are the sheaf of differential operators. So a definition, you define, you fix a positive integer Q, and the sheaf of differential operators that acts on sections of L are elements that are locally on any trivialization are given by a differential operator of degree Q, where the coefficients are holomorphic functions or regular functions, depends in one category you work. So locally, your line bundle is a trivial line bundle on the open set. If you take any section, you can see it as a local function. And if you act by differentiating your local sections, you will get another function. And by identification, you will get a section. So this object can be glued together to have global differential operator with that acts on sections of L. But we are interested in the relative version. So what we need the relative differential operators. Just a remark, a differential operator are C-linear maps. But to construct a relative version, you need to more than this. You need to be pi minus 1 OB linear, which means that you need to be linear for any functions that came from B. In other sense, you are linear for any functions on M that are constant on the fibers. It means that you need to satisfy such an equation. P star H is just H composed by precomposed with pi. If you have an object like this, you have for any Q a sheaf. So in particular, the differential operators of degree 0 are the functions if you have line bundle. And you have natural inclusions. The sheaf of Q minus 1 differential operators is a subsheaf of the Q differential operators, and the quotient map give you an element of the symmetric Q symmetric power of the relative tangent bundle. Here, the symbol map is an ordinary symbol map. You take a differential operator, and the map associate the homogeneous part of degree Q. Two important cases. The first one is the Atiyah sequence of a line bundle. So you take the degree 1, Q equals 1. You will get short exact sequence. And if you fix B in the base, you will get a class associated to your line bundle, which is an extension class. So the space of extension classes will be identified with this cohomology group. So this is what we call the Atiyah class. And the first cohomology connecting map in a cohomology is denoted delta 1 is exactly the cup product with this Atiyah class. So Atiyah class locally is a one form, and a global vector field locally is a vector field. So you can evaluate, but you will get locally a function. And with the gluing conditions, you will get an element of the first cohomology group. Another remark, the first cohomology group on the trivial line bundle is it parameterizes the infinitesimal deformations of line bundle on your manifold, on your variety. So this is, in some sense, the tangent space of the Picard group of MB. Okay. The second important case is when Q equals 2. So you will take the sheaf of differential operators of degree 2, and this is the second order map, sample map. But if you take projective operators, differential operators, which means that you quotient the first sheaf by the trivial line bundle and the second sheaf by trivial line bundle, which means that you define a relation that two differential operators of same degree are projectively equivalent if the difference is a function. So by the Atiyah exact sequence, the quotient of this sheaf by the trivial line bundle is exactly the relative tangent bundle. And in the right-hand side, we have the same sheaf. So the co-boundary map of this short exact sequence take global symmetric vector field and associate the infinitesimal deformation of your complex structure. This map in general we denoted mu of n. So you can define this map globally, but here I prefer to define point by point, just to have an image of vector spaces. So, sorry. So if you do not KMB, it's the relative canonical line bundle, which means the exterior product of the first order differential forms, relative differential forms, and top means the exterior products up to the dimension, relative dimension, so the dimension of the fibers. So this is the dual, as usual, the dual of the relative tangent field. So Welters, Bayer, Bolognesi, Martens, and Polish describe this map globally over B. It can be written as a cup product with the Atiyah class of your line bundle minus 1/2, the cup product with the Atiyah class of the canonical line bundle of the fiber. And the global version of B is you replace the canonical bundle of the fiber by the relative canonical line bundle. So you will get push forward of symmetric vector fields. And here you take the first direct image where the fibers, if you want, is identified with this cohomology group. So this map, it's very important for us for the criterion for existence of a connection on the push forward. Finally, I want to define a notion of heat operator in algebraic geometry. It will use or act on line sections of line bundles. So as usual, as in the beginning, we have a family of complex varieties, and you have a relative line bundle. So you define a special class of second order differential operators. This class contains the first order part is global on M, depend on all the coordinates of M, and the degree 2 part depend only on the vertical coordinates. So the coordinate on the fibers. So this is a subsheaf of global differential operators, and the local section for chart on M, such that the x1, xn are the coordinate on the fiber, and t1, tm are the coordinate that came from B. So H will be written like this. So you have the second order part depend only on the vertical coordinate, and the degree 1 part depend on all the coordinates. And F here is a degree 0 differential operators. And as we are interested just on the projective one, so you can forget about F. Now I can define a heat operator. So a heat operator is an obilinear map over B, where if you take a local vector field on B, it associates to you an element of projective element of this sheaf. So differential operators of this form up where you forget the degree 0 part. But this is not sufficient. You need to ask that the degree 1 part depend only on the horizontal parameter coordinate, and also that the image, the degree 1 part here, that the part that depends on the horizontal coordinates is exactly theta. So it's exactly the image if you want the lift of your vector field theta. So there is a sheaf version of these two conditions, but I will not write it here. So this is you can imagine this definition by analogy with the differential operators in analysis, the standard one. Why we are interested in before this, sorry, if you have a heat operator, we can construct what we call the symbol map, which is associated to heat operator is degree 2 part, homogeneous degree 2 part, and simply you take the heat operator and you compose it with the second order symbol map. The composition is what we call the symbol map associated to the heat operator. Natural question: can we lift any map like this to a heat operator where the symbol map is exactly the map that we fixed before? Well, the answer is no, in general, because the fibers of your map pi are not necessarily products. It's not necessarily trivial fibration. And to do this, Van Giemen and de Jong showed the following theorem: that if you have a symbol map, we call this map the symbol map, you need 3 conditions. The first one, the precomposition of row with the natural map associated to your line bundle gives you minus the Kodaira-Spencer map of this family. The second important condition is that the K-product with the Atiyah class of your line bundle is an isomorphism here. So this is global sections, relative sections, global relative vector fields, sorry. And this is, if you want, deformations of your relative line bundle. And the last condition is just technical. The push forward of the trivial must be the trivial. You can imagine this condition, or if you want, that the fibers of pi are connected. If you have the 3 conditions, you can lift your symbol map to a unique heat operator whose symbol map is exactly what you fixed. So this is a very strong result, because this condition here, the 3 conditions are not in general satisfying. Now, why we are interested in heat operators? So the machinery is the following. If you have a heat operator on your line bundle relatively to base B, you can associate to it a covariant derivative on the push forward. So it means that for any local section on B, you can derive your sections in the direction of theta. And the definition propositions, how you associate, you take sigma theta s to be your heat operator applied to theta, and after that you apply to your section. If you have this, the proposition tells us that this is a connection on the push forward. What you need to show is that's the Leibniz rule. To do it, you apply the definition here, just the definition, but the equality here, it's in fact true only if you have a heat operator. Otherwise, you will have a third part here, third term here, that is not in general zero. So to have the equality, it's just due to the fact that you have a heat operator here. So the condition, the definition of heat operator gives you the Leibniz rule directly. Now, another important thing is that now you have a heat operator. By Van Giemen-de Jong, you can, if you have a symbol map, sorry, by Van Giemen-de Jong, you can construct a heat operator, and to your heat operator, you can construct a connection on the push forward. So you need to study the property of this connection. For example, the flatness. You define the heat operator to be flat if it preserves Lie brackets. Means that if you take the natural Lie brackets of your vector field, with two vector fields on the base, you will get the Lie brackets of differential operators, the standard one. So you compose the two differential operators in the two directions, and you do the subtraction. Another important thing is that, important fact is that if your heat operator is flat, the associated connection is flat. This is a result, and Hitchin itself give us a criterion for a flatness encoded just on the symbol map. If you have a heat operator with symbol map rho, this the associated connection is projectively flat if you have three conditions. I will begin by the third one. Third one tells us that there is no relative vector fields. Means that there is no vector field that fixes your line bundle difference. The second condition is that the natural map associated to your line bundle is an injective map. And the first condition is a little bit technical. If you take the cotangent bundle of the relative cotangent bundle, it's naturally symplectic manifold by the Liouville symplectic form. And rho of theta1 and rho of theta2 for any theta section, local vector field on B, it's an element of the symmetric vector field, but you can identify this space by order 2 functions on the cotangent space. So this Poisson commuteness, it's well defined. If you have the three conditions, you have the flatness. Now we can come back to Hitchin's example. If you have a parameter space B, not only the Teichmüller space, you take a family of curves of genus G. G, we will suppose it's greater than 2. And pi here is a family of relative family of moduli spaces, where for each B in the base you have curve given by Q-1 of B, and MB, the fiber here, is exactly the moduli space of semi-stable rank R bundles over CB that have a rank R and trivial determinant. And L is what we call the relative ample line bundle, which means that the restrictions to the fibers give us exactly the ample generators of the moduli space given by the fiber. And there is a technical condition, I will comment it here. If the rank is greater than 3, you need, if the genus is 2, you need to take a rank greater than 3. Otherwise, if you take rank 2, genus 2, and trivial determinant, the moduli space, it is just P3, and stability, the stable locus do not coincide with the smooth locus. In fact, P3 is smooth, and you have Kummer variety, special variety that contains only the strictly semi-stable bundles, so we cannot apply the criteria of flatness. There is always global sections. So this case, genus 2, rank 2 trivial determinant, was treated by Van Giemen-de Jong, in fact, to complete Hitchin's work. In fact, Hitchin showed the theorem, except the case rank 2, genus 2. And to complete this, Van Giemen-de Jong construct all the theory of heat operators, but they didn't use it to prove Hitchin's theorem. they use it to complete the case where Hitchin didn't do. And the work was done by Bayer, Bolognesi, Martens, and Poli. They took this configuration and they proved that there is a unique projectively flat connection on the push forward induced by a heat operator on the line bundle LK, L to the power positive power K. And to do this, they use a lot of complicated theories, for example, the complex trath theory. And also they show the existence of this heat operator by giving the right symbol map. So in the second part, I will talk about this symbol map and how we can show Van Giemen-Dion criteria, and after that, the flatness criteria. So in the second part, I will talk about the parabolic case. Thank you for your attention.
Thank you, Zakaria.